Hi there and welcome to Lab 8 for Biostatistics. So today we're looking at the linear model again using the donkey data, and it's a little bit different in that we don't have a lab sheet today, so all of the what to do is written in the markdown file here, right? So again, we're looking just at body weight in terms of heart girth, and we'll be able to see sort of how this happens. So this first code block here is again reading all the data in. It's just like we did in Lab 7, reading all the data in, filtering out the horse, right, the one with the large height, and then doing a plot of heart girth versus body weight, right? So maybe we'll just quickly write mostly linear increasing trend relationship between body weight and heart girth. Okay, and then we're going to fit the same linear model that we've done before and do a prediction of a donkey with heart girth 110 centimeters. Okay, so from this we say that so we predict we're 95% confident, or so predict that 95% of Moroccan donkeys with heart girth 110 centimeters would weigh between 95 and 138 kilograms. Okay, so now we're going to look at the model diagnostics of this. Okay, so we're going to assess the diagnostics and see whether the assumptions that we've made, linearity, independence, normality, and equal variance, actually hold in these data. Okay, so this is the most important one, which is the residuals versus fitted plot. Okay, a little bit about this. So the plot command on our object LM1, so LM1 is the name of the model that I developed here, created here. It's LM1 up there. Okay, which equals 1 is just saying which of the plots that I want. So by default, the plot function will produce 4 separate plots that we talked about in the end of lecture 7. This is just picking out the first one, which is the residuals versus fitted, and the last thing here, add smooth equals false, turns off the red line. Okay, so if I turn it back on, you see that red line there. I prefer to turn it off because we shouldn't really be looking at that red line to assess linearity and equal variance. It can sometimes lead our eye a little bit too much. But what we do notice here is that this is not what we would like to see, right? So what we notice is that as you go from left to right on the plot, the residuals are positive. They're above the dashed line at 0. So the residuals are up here. And then as you move across, it drops down and then goes back up again. So you can see the presence of a curve here, right? Which is suggesting that linearity does not hold, a straight line trend does not hold here, and instead a curved trend is more appropriate. The residual versus fitted plot shows us this. And in fact, if we look very closely at the original data, we can actually, now that we know that maybe there's a curve here, you can see that if you fit a straight line through here, it doesn't actually work, does it? There's this very slight curve here that we want to use. Okay, once we know it, we can see it, but it's hard to see by itself, which is, I mean, that's one of the purposes of the residual versus fitted plot, is it enables you to see that curve. All right, so linearity here doesn't hold because we notice that the average residual starts off positive, greater than 0, then reduces, maybe goes negative, less than 0, and then goes positive again as we move from left to right across the plot, i.e. the average trend is a curve. Also, equal variance I don't think holds either. Also doesn't hold. And when we're evaluating equal variance, what we're doing is we're saying, okay, given the trend, whatever it is, so in this case it's a curve, what we want to do is see the scatter around the trend. So how much variation is there around that trend? And you can see there's actually very little variation here. but that we get bigger and bigger variation as we move across, right? As the variation scatter around the trend. So it's just the vertical scatter. We don't care about the horizontal spacing. It's just the vertical scatter in the vertical direction around the trend is increasing as we move from left to right across the plot. So i.e. small variation in residuals for low low body weights, larger variation for higher body weights. Okay, so this is your fitted value, right? So this is your body weight, predicted body weight. Okay. Right, so this is a problem because linearity is the most important thing. It's saying, it's saying that we can't, our modeled average is not correct, right? So, and the linear model is all about modeling the average. So if we don't get it right, we're basically screwed, right? So we're going to try and fix this today by transforming the data. Okay, so what we're going to do is we're going to look at the data on a different scale. So perhaps before we go cracking straight in with the modeling, we might try this in to do a plot first. So let's grab the plot that we did above, right at the start here, and we'll switch to a log axis instead. So what I'm going to do is I'm going to add on scale x log 10, right? That'll put the x coordinates on the log scale, and scale y log 10, which will put the y coordinates on the log scale, right? And you can see here that this flattens things out a bit, right? You can see that this is much straighter relationship than the one I had before, which is curved. Okay. So fitting a straight line relationship to the log of heart girth and the log of body weight will probably give us a nice linear trend. So let's try that. So all we have to do is change body weight to log body weight and change heart girth to log heart girth. I've created a new one, LM2, just so I've got two now and I can compare them, right? So now when you look at the summary, we've got a different equation. So let's write about that. So editor here seems to have been doing odd things. I did this the other day as well. So the equation here is, just going to knit this, see if I can fix up this editor weirdness. Maybe I'll just close it down and open it up again, see if that fixes it. Okay. So the equation here is log body weight equals minus 7.4 plus 2.6 times log heart girth. Right, so it's not as useful to us, or it's a little bit more obfuscated maybe, in that we can't just use simple arithmetic to multiplication and addition in order for a given heart girth to find the body weight. What we're going to have to do is we're going to have to log the heart girth first, then multiply by 2.6 and subtract 7.4, and then we have to undo the log to get to the body weight. Okay, so it's a little bit more complicated, but it is fitting the data better, and we can see that with the R squared has gone up, right? R squared value, multiple R squared value has increased to 0.82 we're now explaining 82% of the variation in body weight by using the heart girth in this model. Okay, so before we were only we were 80%, I think, right? 0.8. Now we're 82%. So we explained a bit more, which is nice. Now let's assess linearity and equal variance. So what we'll do is we'll take that same plot that we did to assess it last time, this one here, and we'll just redo that, but for LM2. So let's see whether the log improves things. Okay, so this is looking much better, isn't it? There's no longer a curvy trend here, is there? If you go through the data, we've got about the same above and below the line. It's near enough to flat. So linearity here looks way better. There doesn't seem to be a curved trend. The trend seems flat. Flat and straight. Equal variance is also looking good. Right? The variation is around about the same. Essentially what you want is you want a picture that looks like this, right? Where the variation is about the same as you go across. Obviously it's going to be slightly different at either end, simply because you typically don't have many observations there, right? We've only got one down here, so you know it can't be too far away from the line, and same up here. But this is the typical shape that you might expect. Okay. So what we'd expect then is that this is a better model all around, right? So we're better estimating the average. The average is going through the data much better. We're also explaining more of the variation by the average, by using the average, which is 82%. So we'd expect our predictions to be more accurate, right? So let's redo the prediction for a 110 centimetre donkey. Okay, here's the predictions. Now, these aren't much use, aren't they? These clearly aren't the weight of a donkey, right? A donkey does not weigh 4.7 kilos. And that's because it's doing the predictions on the log scale, right? The model is for the log of body weight, and we want the body weight. So we're going to have to undo the log, which is exponentiating. So this next line here adds on the exponentiation. Okay, that looks like the weight of a donkey, right? So we're at 95%, confident that 95% of individual donkeys would weigh, donkeys with heart girth 110 centimeters would weigh between 97.6 kilos and 136. Okay, now let's go back and have a look at what we had before. So before, from the previous model, which wasn't as good, our prediction was 95 to 138. Now our predictions are 97 to 136. So they're narrower, aren't they? So this range is narrower than what we had with our first model. This is because we've explained more of the variation in body weight. So there's less leftover variation of the individuals around the trend. So prediction intervals are smaller. Not much shorter though, right? So we've gone from, what was it, 96 to 138 kilos down to 90, near enough 98 to 136 kilos. All right, so we've only reduced the range by 4 kilos. So while it's better, it's not much better. And this is fairly typical of what you find in situations like this, and it's because the linearity of the model was only really bad at the ends. Okay, if you go back and have a look at the original curve, right, you can actually see that if you actually rule out the donkeys that are sort of 90 kilos or less, and you rule out the ones that are less than sort of 100 centimetres in hard girth, and you rule out the ones that are more than about 130 centimetres in hard girth, then a straight line's going to fit really well. Right, so through the middle of the data, where most of the data are, the straight line relationship will actually be reasonably good. Right, it's only really when you get to the ends that it's a problem. And we can see that if we add a smoother, like we did in lab 7, I think, didn't we? With the same mapping. I should copy and paste that, shouldn't I? With a method equals LM. Right, you can see that through the middle of the data that line's fitting well, but at the ends it's underestimating what the body weight should be, and at both ends essentially, right? So these ones are all heavier than what we're predicting, except for this one, and these ones are just about all heavier than what we're predicting as well. And in the middle it's sort of balanced. So you can see that in the middle here, this model will be doing just fine, right? And that's where we're doing our prediction, right? Heart girth 110, right in the middle, smack bang in the middle of the data. And in the middle of the data, the straight line relationship is fine. It works fine. It's only really bad at the ends, right? So this is sort of a common thing that happens in that essentially our models will always be imperfect. They'll always be wrong in some aspect, right? They're not going to be perfectly linear. They're not going to be perfectly equal variance and so on. But for the purpose that we may need to use it for, they might be just fine, right? So as long as we're dealing with typical donkeys, so donkeys in the sort of the middle of the range here, we're going to be okay using the straight line relationship. It's only for the extreme donkeys, the small ones and the big ones, that we're going to be wildly off, right? And we can see this if we repeat this, the prediction process for each model, right? So let's go back here and let's redo this prediction. So we'll just write a little bit about the models. So this is because where we're doing the prediction is right in the middle of the data, where the straight line model does just fine. It's only at the ends that it is having trouble. So the model is okay if all we're using it for is donkeys in the middle of the range. It's only going to be bad, i.e. wrong, for small or large donkeys. Right, so there's a trade-off between model complexity and model correctness. If you want to be correct, your model will be more complicated, e.g. a log model. But maybe you're okay with being a little wrong if it gives a way simpler model, right? So let's try a prediction for a small donkey. Right, so we could use the same codes as we had before. So let's do the prediction for LM1. And then we'll do the prediction for LM2 as well. Right, so we're going to have small donkey. So let's create a small donkey data set where the heart girth is maybe 80 centimeters. Right, so our small donkey data set just has one row with heart girth 80. Let's do the predictions for each of these. Okay. You can see here that the simple model does really badly. It says the donkey is between 10 kilos and 53 kilos, which is almost certainly not true. Right? If we go back and have a look at our data, right, when the heart girth is 80 centimeters, the only observations we've got is over 50 kilos. Right? We're definitely not, don't have data further than that down, and definitely not anywhere near 10 kilos. So that's just ridiculous. And of course, if we could change this, so if we drop it down to 70, we would be ending up predicting that the donkey could be up to minus 18 kilos, which is completely ridiculous, right? So the simple model has constraints. The log-log model, on the other hand, gives us a range that seems more plausible. Okay, and you'll find the same thing at the other end, right? If you predict a donkey with a large heart girth, you'll get the same thing, right? You'll under-predict its weight with the simple model, and you'll get something a little bit more accurate with the other model. So the linearity assumption, the equal variance assumption seems fine here. What about the other ones? So let's just do all of them. So we can do that just by not specifying the width. Let's turn the smoother off. Right, we get 4 plots. So there's the first one, the one we've already dealt with. There's the second one, which is the normal QQ plot. So you remember what I said about this is essentially it doesn't matter. Okay. Ideally, every point would be along the line, but that just about never happens. You usually always get this phenomenon where it sort of veers away from the line at both ends, and usually in the same pattern where it goes down and up here. Okay, and that's just because you're sort of slightly more likely to get more noise down the end, so more extreme observations at the end in your sample. So this is basically perfect. There's nothing wrong with this. The scale versus location plot is just a transformation of this one. So all we do is, instead of plotting the residuals versus the fitted value, you square root the residual first. Okay, so you take the absolute value of the residual, so you get rid of the pluses and minus, and then you square root it. And the idea behind this one is it's supposed to take trend out a little bit, so that you're just left with constant variance. So it's useful for assessing variation. So ideally everything should be roughly in a band, which it is. But usually I find it harder to assess equal variance on here than I do on the first one. So normally I just ignore this one altogether. And of course you remember the last one is assessing leverage. So what we're doing here is, influential outliers is what we're looking for. So what we're looking for is, are any of the points that we see here past these bands down here in the bottom right and the top right? And you can see we have no observations down here, no observations up here. All the observations are in the middle here, so everything is fine. Okay. If we were to have had an observation out here, then that's telling us that that point has large leverage, large influence on the model. So it means that our conclusions are being largely based on that one observation compared to the rest. Right? And at that point, if that happens, then your conclusions are just based on 1 or 2 observations. You should really be a little bit concerned about that. Essentially your sample size is 1 instead of being 300 or whatever. So you should remove that extreme observation and refit your data to the data set without that observation in it. Okay. So that's what to do in that case. And then you can basically look at your model and decide whether your same conclusions hold. Okay. Right, so let's write a little bit about this. So normality looks fine. Most points are along the line in the plot, which is what we'd expect. A bit of veering off at each end, there's no problem. Okay, there are no points with high influence past the, so these are called Cook's distance bands. So no observations with large influence that we need to worry about. What about independence? So independence is something that's hard to check unless you know how the data are collected. So the problem with independence is that, so essentially what you want to know is, are observations more related to other specific observations than to random observations? So you kind of need to know how the data are collected. So for example, if when we went and collected these data, if we had gone, you know, maybe there's actually only three, so maybe there's only 3 donkey breeders in Morocco, right? And so there's only 3 breeders from where these donkeys could have come. Then you might expect donkeys from the same breeder to be more related to each other than they are to donkeys from other breeders, right? Due to genetics or, you know, management during upbringing or whatever, right? That's the type of thing where independence wouldn't hold, right? Because you'd expect donkeys to be more related to each other if they shared a breeder. So in order to account for that, you would have to include breeder in your model. Okay, but once you had included breeder in your model and you'd estimated the random effect, essentially the effect of each breeder, then the residuals, the leftover variation, would no longer be dependent on breeder because you've accounted for it. So you would have been solving the independence problem, the lack of independence problem, right? So when you think about independence, you have to think about how the data are collected. So and whether there's any relationships within the data, i.e. between pairs of observations, that might make them more or less likely to be related than when comparing to other pairs of observations. In this case, we really don't know. So can't really answer this in any detail. I guess what we might be able to say is we might think that, you might think that even after accounting for heart girth, that perhaps there'd be a difference between male and female donkeys. So maybe you'd expect the males to be more similar to other males than you would to other females. So there might be a lack of independence there. Okay, but of course we could account for that in this model, right? Because we could just add sex as a covariate into the model. We'll see how to do that in lecture 9 and in lab 9 as well. In lecture 8, we'll see how to do that. But generally, independence, lack of independence is something that that is kind of external to the data. So it's something about the way the data were collected that you haven't accounted for in your model. That's basically what it comes down to. Okay, I'm just going to knit this, make sure it works. That looks okay.